Now, in this lecture, I'm going to look at the uniform distribution, in particular, the continuous uniform distribution. The sample space of this distribution is an interval. That is why the random variable that has this kind of a distribution is called a continuous uniform distribution as opposed to a discrete uniform distribution. So for a given uniform distribution, there are two parameters essentially, the lower and upper endpoints of the interval over which the probability density is distributed uniformly. And here obviously A is strictly less than B. The probability density function is given by the following expression. For values of x between A and B, the PDF, the density, is equal to 1 over B minus A, and it's 0 otherwise. And this is very easy to derive because by definition, the probability density has to be uniformly distributed across this interval. So that would require then that this be the density for values of x between A and B. Now, when x has a uniform distribution on an interval, AB, we're going to denote that this way. So using the conventional notation, the random variable that we're talking about, and then a tilde, which is an abbreviation for is distributed as, and then the name of the distribution, which is, in this case, the uniform, and then the interval over which the probability density is distributed. And so it's asking us to find the cumulative distribution function, the mean, the variance, the standard deviation, skewness and kurtosis, and the moment generating function if we can. But in all honesty, in this case, for this distribution, we really don't need the moment generating function. So I'm not going to bother doing that. And so anyway, denote the CDF of the random variable x by cap f. Now, since the space of x is the interval from A to B, the open interval from A to B, we can conclude immediately, without really having to do any work, just appealing to the definition of the CDF, which remember is a probability accumulator. The CDF is going to evaluate to 0. If we evaluate it at any value of x that is at or to the left of the lower endpoint, the lower boundary, let's say, of the interval. And it's going to be 1 if we evaluate it at any value of x that is greater than or equal to the upper boundary of the interval. Now, for values of x that are greater than A and less than B, in other words, for any value of x in the sample space of the random variable x, then the CDF is given by the integral from minus infinity up to the argument of the CDF at which we're evaluating it, so x, of the PDF. And again, notice that the variable of integration cannot be x. It's got to be something different, so I'll use t in this situation. All right, this simplifies to the integral from a up to x, and over that interval, the PDF evaluates to 1 over b minus a. Because that does not depend on the variable of integration t, we can pull that outside of the integral, and so we're left with the integral from a to x of dt, which is very easy to evaluate. The antiderivative, we're essentially evaluating the function equal to 1, which I've just left out there. 1 times dt is just dt, so we don't need to write it there. The antiderivative of that is just t. We evaluate that at x and at a and then take the difference. All right, and again we have to multiply by the 1 over b minus a. And so for values of x between a and b, this is the expression for the CDF. And so putting these results together, we have here the fully specified expression for the CDF. Again, for values of x that are less than or equal to a, the lower endpoint of the interval, that is the sample space, the CDF evaluates to 0. For values of x that are greater than or equal to b, the upper boundary of the sample space, the CDF evaluates to 1. And then for values of x between a and b, the expression for the CDF is x minus a over b minus a. So think about what, what a function of that CDF looks like. And also, while you're at it, think about what this function of the PDF looks like. See if you can graph those. Now, the mean and the variance of the distribution. I'm going to leave these as an exercise for you. They're very straightforward to find. The integrals that you would have to evaluate to find these values, or these expressions, for the mean and for the variance, are fairly straightforward. So I'll leave that for you. It can be shown that the mean of the distribution, the expected value of x, is equal to a plus b over 2. This is the midpoint of the sample space, the midpoint of the interval from a to b. And then the variance of x is equal to b minus a quantity squared over 12. This is the square of the length of the interval divided by 12. Also, and I'm not going to give you formulas for these, I'll let you try to figure these out as kind of an added incentive here. If you want to see what these expressions are, you're going to have to do the work to get there. So I'll let you try to find the skewness and the kurtosis. You have the mean and the variance here, and so you can start off by seeing if you can derive these same expressions, and then go from there and see and come up with some expressions for the skewness and the kurtosis. All right, so let's look at an example. And so suppose that a car travels between two cities, A and C, which are 75 miles apart. If the car has a breakdown, the distance, which we'll denote by x, from the breakdown to city A is, in this problem, assumed to have a uniform distribution on the interval from 0 to 75. So if the car has a breakdown, then we let x be the distance that the car is from city A at the point of the breakdown. Now, the driver is a member of an automobile service that has contacts with garages in cities A, B, and C, where city B is between cities A and C, and it's located 25 miles from city A. Now, according to the service contract, or the automobile service contract, if the car breaks down, it will be towed to the nearest city. And so we want to use this information to answer the following questions. The first question, find the probability that the car is towed more than 10 miles if it happens to break down. The second question, if the car breaks down, find the probability that the car has to be towed more than 20 miles. And then finally, if the car breaks down, find the probability that the car is towed more than 10 miles, given that it is more than 20 miles from city A. Now, for all these, it's going to help to draw a picture, and that's typically what I do when I'm doing this live in class. Put some, draw on some pages on the overhead. All right, so I'm going to let you do that. But let's write down what we know, and then see if we can go from there. So we're told that x, which is the random variable x, which is the distance from city A, if at the point or when the car breaks down, and we're told that this has a uniform distribution on the interval from 0 to 75, and the units here would be miles. And so, given that information, that x has this distribution, we can immediately write down the PDF and the CDF, because we know the general forms for these functions. And so the PDF of the distribution of x is equal to 1 over 75 for values of x that are between 0 and 75, and 0 otherwise. The CDF is 0 if x, the argument that we're evaluating it at, is less than or equal to 0. It's 1 if x is greater than or equal to 75, and it's x over 75 if we evaluate it at a value between 0 and 75. So let's look at the first question. Find the probability that the car is towed more than 10 miles. So if the car breaks down, what is the probability that the car is towed more than 10 miles? And so the probability, or let me say it this way, the event that the car is towed more than 10 miles can be decomposed into the union of two events. And this is where drawing a picture, a very simple picture, will suffice, but drawing a picture will help you see this. But the event that the car is towed more than 10 miles is the union of two events. The first event being that x, the distance from city A when it breaks down, is between 10 and 15 miles. And the second event is the event that it breaks down somewhere between 35 and 65 miles from city A. And so the car will be towed more than 10 miles if and only if the breakdown point is between 10 and 15 miles from city A, or if it's between 35 and 65 miles from city A. So we have here the probability of a union of two events. Those events, you will agree, are mutually exclusive. They cannot both happen at the same time. The car cannot break down at a point that is between 10 and 15 miles from city A, and also between 35 and 65 miles from city A. Those two events are mutually exclusive. And so by axiom 3, we can decompose the probability of the union as the sum of these individual probabilities. Okay? Now, in going from this step to this step, notice that I've changed the inequality here from a strict inequality to a non-strict inequality, and I've done the same thing here. Now, you'll remember from the previous lecture, we can do this because the random variable x is a continuous random variable. You cannot do this if you're dealing with a discrete random variable, because changing the inequality from strictly less than to less than or equal to can change the probability, but it's not going to change the probability when we're dealing with a continuous random variable. So it's perfectly acceptable in this situation to change that inequality there and there. Now, the reason I want to do that is because it's very easy to calculate this probability here using the CDF. This is just the CDF evaluated at the upper endpoint, 15, minus the CDF evaluated at 10. Likewise, the probability that x is greater than 35, but less than or equal to 65, is given by the CDF evaluated at 65 minus the CDF evaluated at 35. And so it becomes very easy to find this probability, and it turns out to be 7 over 15, which is just slightly less than 1/2. Next, let's find the probability that the car is towed more than 20 miles. Now, again, a simple picture will help you to very easily and very quickly see that the event that the car is towed more than 20 miles is equivalent to the event that the point at a breakdown is somewhere between 45 and 55 miles from city A. Now, again, because x is a continuous random variable, I can change the strict inequality to a non-strict inequality. And once I have it in this form, then I can use the CDF to evaluate the probability. It's the CDF evaluated at the upper endpoint minus the CDF evaluated at the lower endpoint. And so that gives me 55 over 75 minus 45 over 75, which is 10 over 75, or 2 over 15. All right, and then finally, find the probability that the car is towed more than 10 miles, given that it is more than 20 miles from city A when it breaks down. Okay, so here we have a conditional probability. And so in order to facilitate putting this onto a slide that has limited space, let me define two events, A and B. So A will be the event that the car is towed more than 10 miles, and B will be the event that the breakdown occurs when the car is more than 20 miles from city A. Now, the first thing I need here is to find the probability of the conditioning event, the probability of B, expressed in terms of the random variable x. The event B is the event that x is greater than 20. And so we want the probability that x is greater than 20, which by the complement rule is equal to 1 minus the probability that x is less than or equal to 20. All right, and so this is the type of probability that we can calculate using the CDF. All right, it's just the CDF evaluated to 20. And so this probability is 1 minus 20 over 75, which is 55 over 75, or 11/15. Next, note that the probability of the intersection of these two events, A and B, let me back up. The event A intersect B it turns out to be equivalent to the event that x is between 35 and 65. All right, so again, think about what these two events represent. Draw a picture, all right, and you'll see that the intersection of those two events is the event that x is between 35 and 65. So this is the event whose probability we want. And again, because x is a continuous random variable, we can change the strict inequality to a non-strict inequality. And then once we have done that, then we can use the CDF to evaluate this probability. And it turns out to be 6 over 15. And so finally, we can use the definition of conditional probability. We have calculated all the ingredients we need to calculate this conditional probability. By the definition, the conditional probability of A given B is equal to the probability that both A and B occur divided by the probability of the conditioning event. So we have 6 over 15 divided by 11 over 15, and that simplifies to 6 over 11. So a little bit more than, that's a little bit more than 1/2. Okay, so that's how we can calculate probabilities. And notice that we have not had to resort to doing any integration to calculate these probabilities, even though x is a continuous random variable. And the reason is because we've been able to express all of these probabilities in terms of the CDF. The CDF is where we actually had to do the integration. All right, but once we've done that, in many cases, we're not going to have to do any more integration. All we have to do is appeal to and use the CDF that we've already constructed. Okay, and then finally, what we could answer questions like what is the expected distance at which a car would break down? Well, if x is uniformly distributed from 0 to 75, then the expected value of x would be 0 plus 75 over 2, or 37.5. So that's the expected distance. If the car is going to break down, that's the expected distance at which it would break down. What's the variability of x? Well, that's the square of the length of this interval. The interval has length 75, so we square that and then divide by 12. And so this would be 468.75. By the way, let me go back here. The units for the expected value of x, obviously, is miles. Going back to the variance of x would be 468.75 miles squared. All right, and to get back to a measure of variability that has units that are the same as the units of the random variable, we can use the standard deviation, which is the square root of the variance. And so the standard deviation of x would be 21.65 miles. All right, so that's really all I'm going to say at this point about the continuous uniform distribution. What I would do is go back here and make sure that you can derive the mean and the variance for the continuous uniform distribution. And once you get that down, take a stab at the skewness and the kurtosis of the distribution, which I'm leaving as an exercise.